So before we stop, we talk about this gamma. This is the definition of gamma, and you can see in order to be a coordinate transformation and in order to compute this Poisson bracket, you need to know how the new variable E and A depend on old variable E and K. So of course E is dependent on E, and A should depend on both E and K. And so here A depends on K linearly, but A depends on E non-linearly. And because gamma depends on E, gamma is just a function of E. Yeah? But this formula only has gamma depends on little e, this small e. So which means you have to use capital E to express the little e. And you will get some formula which is a little bit more complicated than this. I'm not going to show you, but this formula you can find in the book. So see Timan's book. Timan's book. The equation 4.2.18 for the expression gamma IA as a function of E, as a function of capital E. Yeah? And you are going to use this formula and work out this homework. So basically, this homework is just let you to derive the Poisson bracket between E and A. Compute E A B Y and A and A. Okay, and you don't need to compute E and E because it's the same as before. It's the same as previous EK in EK phase space, in EK Poisson bracket. Okay, compute using Poisson bracket. Poisson bracket in terms of EAI and KJB. Yeah. So okay, just so the purpose of this homework is just convince yourself for convincing yourself that these coordinate transformation is indeed a canonical transformation. So you should, by working out this homework, you should be understanding what we mean by canonical transformation. Okay. So now I think it completes the definition of this Ashtekar-Barbero connection, this variable AIA. So this is equals to gamma plus beta k. K is just extrinsic curvature, and gamma is a spin connection. It's a function of E. Okay. So then why it is so good about this new variable? So it is nice when we express the constraint. So we are going to discuss constraint in terms of new variables. In terms of new variables. Okay. So first, the simplest constraint is the Gauss constraint. So let's first Gauss constraint. Okay, and this Gauss constraint Gj, right? And on the constraint surface, this Gauss constraint equals to 0, and Gj by definition it is beta. Well, I mean, before it has no beta as a coefficient, but right now I just rescale the Gauss constraint by adding a beta. Well, constraint multiply a constant is still a constraint. EAL. Okay, but of course I'm freely to plus a 0 in front. Okay. Well, I'm so I freely I just plus a 0. It doesn't change anything, but this 0 can be expressed by in terms of E. So this equals to that. I can write this 0 as the following. So partial A EHA plus epsilon JKL AL. Yeah, plus the term which is non-zero, which is the previous constraint. Yeah. Okay, I just add a 0, so which means this term actually equals to 0. So this is actually coming from the definition of gamma. Yeah, and if you understand, well, it is immediately you should be able to see it if you can understand this formula, if you can understand the meaning of well, this formula. Yeah, if you can understand this formula, you should be able to see it. You should be able to understand that quantity equals to 0 really immediately. If you suppose you understand what we mean by this covariant derivative, and combining the fact that this E is a density. Well, but suppose well, at the moment, and I'm just going to leave you as a homework to check. You can just plug in definition and check if this is explicitly this guy equals to 0. So just your homework is check this. Check this. Something you may need to be careful is that this E is the density. So careful. Yeah, EAJ is a density of weight 1. Weight 1. Yeah. So you may have to be careful in the calculation that E is the density. Or actually, if you are not even careful about it, if you just plug in this definition in the formula, I guess you will still get the result. But anyway, so if you are able to understanding the meaning of the covariant derivative I defined above, you should be able to understand this. But if you are not able to, if you are not familiar with gauge theory and covariant derivatives, but you can still understand this by just by checking explicitly calculate this formula. Okay, and this formula actually so this means that the covariant derivative dA EAJ equals to 0. Yeah. So this is actually related to also the compatibility between the covariant derivative and the metric or also normal basis. Okay. All right. So then we have rewritten these Gauss constraint by just adding a 0. Okay. But why it is so good is because you can combine these last two terms. And if you combine last two terms, you find the first term give you a gamma, and the second term give you a beta times k. And then you immediately combine into a Ashtekar connection. So here you find that Gj equals to partial A J plus epsilon JKL A AL. Okay, and you can write this guy to be a new covariant derivative dA act on EAJ. Yeah. And this new covariant derivative is with respect to this A. Yeah, so you can, well, it is just formal. You can just formally consider it is a new covariant derivative, but and because it is formal at this moment, because I haven't tell you the gauge transformation for A, so it is coming in a moment. But the end, so it ends up to be just a covariant derivative, certain kind of covariant derivative. Okay, so and from this, once you believe that it is a covariant derivative, certain kind of covariant derivative act on E, you can see that this is really analog of Gauss constraint in electromagnetism, analog of Gauss's law in electromagnetism. Okay, because Gauss's law. So you can see the Gauss's law in Maxwell equation. This is just a constraint equation. This has no time derivative. And indeed, if you consider the electromagnetic field and use the Lagrangian and perform the Hamiltonian analysis, like we did for general relativity, and it's of course much simpler than general relativity, and you find indeed that this Gauss's law is a constraint, and it generates gauge transformation, which is just the U1 gauge transformation of the electromagnetism, and then this guy you can see is just the derivative act on E, that is the divergence of E, the covariant derivative contract is a dot product with E, and here you can, it's the same, it's a covariant derivative dot product with E. Okay, but you still have a J index because in our theory the gauge group is not just U1, it is SU3, or it is SU2 gauge group. So the gauge group is non-abelian, so then you get additional index. So yeah, well, I mean, if you, for most of you, you have learned gauge theory in my previous class, you should be able to understand this, I guess. Yeah, for those of you who have no experience on gauge theory, and you can just consider this is the definition of the Gauss constraint, and yeah, you see everything you can derive explicitly. All right, so then this is the Gauss constraint. You can derive the you can express the Gauss constraint in terms of E and Ashtekar-Barbero connection A, and you can also re-express other constraints, for example, the diffeomorphism constraint. Diffeomorphism constraint and CA. After the derivation, you can see that it equals to kappa 2 over kappa Fi AB J divided by beta minus, well, I'm going to put a beta here. So minus a term which is proportional to Gauss constraint. Okay, so this is the if you derive from the ADM diffeomorphism constraint, you will end up with this formula, and you can see that on the constraint surface, because there's a term proportional to Gauss constraint, so therefore on the constraint surface of Gauss constraint, this is just equals to 2 divided by kappa beta Fi AB Bj. All right, so this is the diffeomorphism constraint. So what is this F? This F is the field strength with respect to A. So of course, again, I haven't talked about the gauge transformation for A, but so at this moment, I just ask you to believe me that A is a gauge potential, like I claimed at the very beginning. A is a gauge potential with gauge group SU2. And then once you have the gauge potential, of course, you can define the field strength in non-abelian gauge theory. And this is the definition. And if it is the first time you see this kind of field strength, then you just take it as a definition. Otherwise, for some of you who have seen it before, then of course you should be able to understand it better. Yeah, okay, so this is the definition of F. So well, usually I probably in my gauge theory class, usually I would write F as a matrix equals to partial AB minus partial B A plus a commutator AB. So in case we consider A is the Lie algebra valued or it's a matrix valued, right? And so F is also matrix valued, and then here it is commutator. But you can see that once you use a basis in the Lie algebra, and this commutator gets reduced to the quantity upstairs, and because here the basis is just the Pauli matrix, and the commutator of the Pauli matrix give you epsilon. Okay, and so this guy, it is a what we call field strength, or it is also called curvature two form. Curvature two form. Yeah. So it's the name of F is very much dependent on your background. If you are field theory background person, and then you will call it field strength. If you are geometry background person, you will call it the curvature two form. But they are really the same thing. Also the field strength. And similarly for A, if you are a field theory background, you will call it a gauge potential. And if you are a geometry background person, you will call it a connection. So, but they are the same thing. Field strength by viewing ABJ is the gauge potential. Gauge potential in, so being a gauge potential, this is in the adjoint representation of the gauge group. SU2 or SO3. Adjoint representation of SU2 and SO3 is the same, because this is just a representation. Well, it is not exactly the same. The representation space is the same because it's just representing on the Lie algebra, and the Lie algebra is the same. Yeah. So before I call this IJ by relating to gauge theory, they are flavor index. So they are some kind of special flavor index because they are just because ABJ is a gauge potential, and the gauge being a gauge potential, J index is an index in the adjoint representation. So this is not any flavor index. It is the adjoint representation index. This is a special flavor index. Yeah, because being gauge potential, this is it's in the representation, in the adjoint representation. Okay. Review your gauge theory class. Okay, I think that's all for diffeomorphism constraint, and then for Hamiltonian constraint, you can work out. You can re-express the Hamiltonian constraint in terms of A and E. Constraint. So this is C equals to 1 over kappa F A B J square root Q J K E K E A K E L. Okay, so this is the first term. You have, so the feature of the Hamiltonian constraint here is that you have two terms. Well, you have two important terms. 1 over kappa, the second term. Then you have something relates to Babel image parameter beta square plus 1 epsilon j m n k m a k m p well, and multiply another factor. Well, the multiply this factor is the same as the factor in the first term. Q epsilon E L. Okay, and also you have plus plus terms proportional to Gauss constraint. GJ. Yeah, you have, so if you derive from ADM formalism the Hamiltonian constraint, and you will express everything in terms of A and E, and then you will get firstly these two terms, and then plus multiple terms, which is proportional to Gauss constraint. Yeah, so which means on the constraint surface, you can just ignore the Gauss constraint, the term proportional Gauss constraint. So which means the first two terms is the most important terms, and each term has some special name. And the first term, this is called Euclidean Hamiltonian constraint. Well, let's call it, this is Euclidean term. This is called the Euclidean term in the Hamiltonian constraint. Yeah, but why it is called the Euclidean term is because suppose you are doing a Euclidean signature, gravity in Euclidean signature, and then you do the same Hamiltonian analysis, but then because the metric is in Euclidean signature, some term you will get some minus sign in front, and then you end up with a Hamiltonian constraint. Here, you will get a minus sign for the Euclidean. You will get minus for Euclidean theory. Euclidean theory. Yeah, so namely, you consider a metric is in Euclidean signature. It's a Riemannian metric. You view that is the general relativity. Of course, this is of course a toy model, but you can do that. And then suppose you do that, you will end up with minus sign here, and then you can see that if you write beta, if you consider beta is just a free parameter, Babel image parameter is a free parameter at classical level, and you can just put beta equals 1 and then cancel the second term, yeah, and you're left with the first term. So which means for Euclidean theory, you can have just a very simple Hamiltonian constraint being the first term, right? And that's why the first term is called Euclidean term. But here you can see that for Lorentz signature, it is plus. It is plus sign. Then you are not, for any real beta. By the way, I should have emphasized that beta is a real parameter. It's a real Babel image parameter. Real beta is a real parameter, so A is also a real field. So here you can see that for Lorentz signature, for Lorentzian general relativity, you are not able to set beta to any value, so to cancel the second term. Well, except you put the beta equals to I, right? And indeed, historically, it is actually the first set of Babel, the first set of Ashtekar new variable when Ashtekar first published his paper in 88 or 89, 88 probably, I don't remember. So when in his first paper, he indeed put beta as I. The purpose is just to cancel the second term. Yeah. So the price, of course, the price to pay is that beta is purely imaginary, and the Ashtekar connection become a complex field, and the gauge group is not anymore SU2 but Lorentz group, but SL2C. Okay. Yeah. But then it turns out that for that set of variables, the quantization is very hard to carry out. The quantization is hard, although apparently you cancel the second term, the Hamiltonian constraint become very simple. That was the purpose of Ashtekar at the very beginning. But it turns out it's not really simplifying. It's actually complex, make things even more complicated. And then in early 90s, people find it's too complicated to work out the complex Ashtekar connection. But then Barbero introduced his real Ashtekar-Barbero connection and using real beta. Yeah, and then it turns out that using the real variable, although you get some additional term in the Hamiltonian constraint, and the second term is called a Lorentz term, by the way. Although you have the second term, this is called the Lorentz term. It's classically, it seems that you get a little bit complication, but it turns out quantum mechanically, you can still manage to quantize this term. Yeah, it caused some complication, but manageable. But if you use a complex Ashtekar connection, it's really not manageable. At least it's open issue. Nobody can quantizing the complex Ashtekar variable satisfactorily. All right, so this is the expression of diffeomorphism constraint and Hamiltonian constraint in terms of new variable, and also Gauss constraint in terms of new variable A and E, and those formulas are very, very important, and therefore I would invite you to check as your homework, check these two formula. Yeah, so let me write the homework. Check. Well, let me say this. Derive CA and C, the diffeomorphism constraint and Hamiltonian constraint in terms of A and E, in terms of Ashtekar new variable. Okay, of course, it will be a little bit messy, especially when you're deriving Hamiltonian constraint. So in case you have some difficulties for deriving it, so give you the reference. All the derivation is already in the reference, and you look at the reference is of course Thomas Tiemann's paper, Thomas Tiemann's book. The name, yeah, I have written the name before, the modern canonical quantum general relativity.
Okay. I have a question here. So to find the computation surface, we need to set the Euclidean and the Lorentzian equal to the bracket, right?
Can you say it again?
I mean, to find the computation surface, we need to let the Euclidean and the Lorentzian equal to 0. This break, right?
The constraint surface. So, okay, the constraint surface is all the constraint equals to 0. It's but it's not individually term equals to 0. So the entire constraint surface is defined by, of course, Gauss constraint equals to 0, diffeomorphism constraint equals to 0, and Hamiltonian equals to 0. So, but it's not individually two terms equals to 0.
Oh, okay, got it.
Yeah. So I ignore. So usually the formula for Hamiltonian constraint, diffeomorphism constraint, ignores the terms of Gauss constraint because you have a bunch of terms in terms of Gauss constraint. So I'm usually in formula we just ignore them because we have the Gauss constraint already. Yeah. So we just ignore. It doesn't mean that it's not there. We just don't write it because Gauss constraint equals to 0 anyway. Okay. Okay. Oh, by the way, so here you can see that in the expression of Hamiltonian constraint, I still use K in the expression, but I just but clearly Hamiltonian constraint should be expressed in terms of A and E. But to put still put a k here, I just don't want to. It is standard formula, and we don't want to make a formula longer. But in principle, here it is not explicit. It's not explicitly to write k here, but k has to be k here is actually written as equals to beta a minus gamma ma. Okay, so here k is not really k, but actually this expression, because all in this formula you should express everything in terms of a and e. So this k is written in terms of a and e using the definition of Ashtekar connection. And so it is a minus gamma divided by beta, and here this gamma is a spin connection, it's a function of e only. Yeah, so this is something in your homework you will try to derive them. Okay, so that's all the constraint. And then the Hamiltonian. So here the Ashtekar Navarro Hamiltonian. Hamiltonian H here equals to just a linear combination of those constraints. These three x. CA plus NC. Okay. Yeah, and then the Hamilton's equation, of course, is the same as before. Well, the equation of motion. So for any function f as a function of a and e, the time derivative is just given by the Poisson bracket equals to the Poisson bracket with the Hamiltonian. Okay, and this is the equation of motion, and you have to combine those equation of motion with those constraints. Yeah. And the constraint is preserved by equation of motion. Yeah, and same logic as ADM formalism. They are just equivalent to Einstein equation, and similar here. So you get equation of motion which are completely similar to Einstein equation, completely equivalent to Einstein equation, but you just use a new variable to express those equations. And those equations contains time evolution equation, those Hamilton equation, and the constraint equation. Yeah. The constraint equation has Gauss constraint, diffeomorphism constraint, and Hamiltonian constraint. All right. So yeah, the picture is also similar. Well, similar to ADM formalism. You have the entire phase space in terms of A and E. Okay, so now you have a new phase space in terms of E and A. Okay, and you have the constraint surface. You have constraint surface, and on the constraint surface you have G J equals to CA equals to C equals to 0. This is the constraint surface. Constraint surface, and also on the constraint surface, you have also gauge orbit. Well, the point that the gauge orbit all along the constraint surface is that all those constraints are first class constraints. Remember when we talk about ADM, that all the constraints, well, which are diffeomorphism constraint, Hamiltonian constraint, they are all first class. And here we have one more constraint, which is Gauss constraint. Now I'm telling you that they are also first class. I'm going to show you in a moment. So all those constraints are first class constraint. And then because of their first class and all this, all the gauge transformation are leaving the constraint surface invariant. So all the gauge orbit are lying on the constraint surface, and this is the constraint surface. But then you can, next thing is to define the reduced phase space, right? And the reduced phase space is just a quotient space, yeah? And for every gauge orbit is just a point on the reduced phase space. Okay, and you can also check by counting degree of freedom as we did before, by taking the phase space A and E, count the dimension, and removing the constraint, removing the dimension of the constraint, removing the dimension of gauge transformation, and then you will end up with the dimension of reduced phase space. You will find the reduced phase space should have the same dimension as in ADM formalism, right? Because that must be the same. Otherwise, it won't be consistent. Yeah, and this is so I leave this as an exercise for you to do, just to counting the dimension. Maybe it's good to give you as a homework. Yeah. Homework. Count the dimension of reduced phase space. Space. Yeah, you should get 2 per point. Yeah, you should end up with 2 polarization of graviton. All right. So now I'm going to. By the way, so another thing to mention is that this Hamiltonian. So here we get this Hamiltonian from ADM formulation and then extending the phase space and making canonical transformation. Okay. And there is a way to get this Hamiltonian more directly from an action principle. So before we are using Einstein-Hilbert action to make 3+1 decomposition and derive the ADM formula, right? And actually there's another Lagrangian if you do the well, that Lagrangian is called host action. It's called host action. Well, it's firstly invented by Host. And if you start with this host action with the 3+1 decomposition, and you will end up with this Ashtekar barrel. You will end up with Ashtekar barrel. Okay, and if you are curious about what is host action, so you can just search online. There's a paper by Host. You can find the derivation of that paper. Okay. Well, and this host action, it is equivalent. Well, it is so-called on-shell equivalent to Einstein-Hilbert action. So, which means that if you derive equation motion from host action, it's completely equivalent to Einstein equation. Okay. All right. So let's having those constraints. Let's work out the gauge transformation. So